let's think about a cyclic process. So an ideal gas that goes from some value of volume, let's call it V naught, and some initial value of pressure, P naught. It goes upwards in the diagram to a greater pressure, P1, at constant volume. So we're dealing with an isovolumetric process here. Then we decrease the pressure down back to P naught, but we increase the volume. And we imagine doing this in an such that the temperature is always the same. So here we have isothermal. Here we said it was isovolumetric. And then we'll imagine compressing. So, sorry, we come down and we increase to a volume, let's call it V1. And then we compress the gas back down to the initial volume, which is V naught, at the same pressure. So this is an isobaric process. Okay, so basically this is the kind of thing that engines do. Their device is designed to do work. And so let's evaluate the work that they do, given the constraints of the first law of thermodynamics. So we're dealing with an ideal gas here, so that's true. Let's see what kinds of quantities we get at these various points. Let's call this A, this B, and this C. And let's notice that at point A, we have P naught V naught is equal to NK times TA, and therefore TA is P naught V naught over NK. At point B, we have pressures P1, volume is still V naught, and therefore that's equal to NK times the temperature at B, and therefore TB, the temperature at point B, is equal to P1 V naught over NK. And we can notice that TB over TA is equal to P1 over P naught, which of course is greater than 1. At point C, we have P naught and V1 now, and that's NKTC by the ideal gas law. TC, which given the condition there is TB, which is P naught V1 over NK, which is P1 V naught over NK, right? Because TB is this, and so TC, which must be this by the ideal gas law, is equal to that. And so what follows from this is that P naught V1 is equal to P1 V naught. Okay, so at A, B, and C, we get these various quantities from the ideal gas law. Let's look now at, let's get another sheet. Let's look at what the first law of thermodynamics tells us. So we have delta U equals Q plus W. And at point A, we can say that the internal energy is equal to 3/2 NKTA. That's 3/2 NK. Right, look at TA from the previous page. That's P naught V naught over NK, and therefore we have 3/2 P naught V naught. In terms of the known P naught and V naught, that's what the internal energy is. At point B, the internal energy is from this, it must be TB, which in terms of the known quantities is 3/2 NK. Let's replace TB with the value that we got previously, P1 V naught over NK, and therefore we have 3/2 P1 V naught. At C, the internal energy is 3/2 NKTC, which is 3/2 NKTB, which is, again, 3/2 P1 V naught. Right, the internal energy hasn't changed from point B to point C because it's an isothermal process. The temperature hasn't changed. So let's see. So then we go back to A. Of course, at point A, we again have UA equals 3/2 P naught V naught. Let's look at the work. So the work is something that's defined between states. So the work in going from A to B is 0. Right? We haven't changed the volume. In going from B to C, we have that the work is minus V naught to V1 PdV. We have to integrate this. And this is NK. Well, let's evaluate this. We'll evaluate this in a moment, but let's point out that this quantity is, of course, negative because the P is always positive, and we've written it so that the volume goes from a smaller value to a higher value. So we're dealing with expansion. And then the work from point C to point A is P naught, where we're going V1 to V naught, and this is positive because we're compressing the gas. Okay, so now let's think about the heat. So the heat in going from A to B is equal to, delta U, right? Delta U in going from A to B, which we evaluated, minus W from A to B, right? So delta U is Q plus W, so we can get Q from our difference in internal energy and our work. And we have these quantities evaluated, and this becomes 3/2 P1 V naught minus P naught V naught. The work is 0. And heat in the process going from B to C is B to C, we have delta U, B to C, minus work, B to C. And so this is B to C. There's no change in temperature. That's an isothermal process, so it must be minus B to C for work. and that's equal to, we get rid of the minus sign, V naught to V1 of P dV. And here we can evaluate this, right? It's P is, well, it's by the ideal gas law, and K T, and T is always a constant, and it's the value at TB remains constant, divided by the volume. That's what the pressure is. The pressure is changing with volume, right? We're integrating in the volume from V naught to V1. And so this becomes N K TB, which is P1 V naught over NK. That's a constant, integral in dV over V from V naught to V1. And that's P1 V naught, P1 V naught. Now we integrate this, we get the log, the natural log, and we evaluate it from V1 to V naught. That's, we could write this as log of V1 over V naught, but here it's a little more straightforward to see that this is a positive quantity. Okay, so Q, and so now we have Q C to A is equal to delta U CA, or C to A, minus W C to A, and that is 3/2 P naught V naught minus 3/2 P naught V1 minus P naught V1 minus V naught. And this is 3/2 P naught V naught minus 3/2 P naught V1 minus P naught V1 plus P naught V naught, which is 5/2 P naught V naught minus 5/2 P naught V1. Right, we use the condition that, let's just bring it back, that P1 V naught equals P naught V1. Okay, so where are we? 5/2 here, so this is, let's write this as 5/2 P naught V naught minus V1, and that is clearly negative. And so let's summarize by noticing that delta U total, we're at the same place in the PV diagram, so this is 0. We come back to the same temperature. Delta U is 0, and W total is equal to WB to C plus WC to A, which is P1 V naught, natural log of V naught minus log of V1, plus P naught V1 minus V naught. And finally, the total heat in this process is delta U total minus W total, which of course is minus W total, because we're back at the same place, and so that's just P1 V naught log of V1 minus log of V naught minus P naught V1 minus V naught. So we came back to the same state. Internal energy is back the same, and we have work and heat that are opposite of each other.